Okay, yeehaw.
So I'm like, well,
And let's mute that. Let me just make sure that it's running. Looks like it is. Running. Oh, no, that's just a different thing. Cool. So let's get this going. Here are the topics we're going to cover. I'm just going to review it again for you guys really quick. It's not. What's going on here? Let's actually pull up the right thing, potentially. One day I will have all of this figured out, but it is not now. Is this bringing you flashbacks to, like, yeah. Let's get that quality up. And there we go. Okay. I think we're in a good spot now. Yeah, that'll be absolutely worth it. Okay. So once again, we're going to review E and V operators, covariance, correlation tips and tricks. That's going to be a review for you guys. Also the K thing. And just like normal PDFs, and by normal PDFs I mean like the standard just like probability distribution functions that we started with before the first midterm, that's all going to be review. But then we're going to go for stuff like the density functions and the joint functions and the, the conditional functions and the marginal ones and all the stuff that we've learned since the midterm. Then we'll talk about Bernoulli, uniform, normal, chi-squared t distributions, all the fun special things that have to do with those. And then we'll do some special tricks and wizard magic. And then we'll talk about reading the charts, because learning how to read the charts is actually, and how to like think about the graphs and the charts and everything on there is critical. It's basically the rest of the class. And it's actually these skills that like the class was designed for. So let's get right into it. Let's start by just chatting for a second. Some quick reminders about how to pass through expected value, and also if you guys have any questions, let me know. And then I'm also just going to pull up really quickly the chat so that if someone's got questions in the chat, I will be able to see those, although you do have to be subscribed to be able to chat, which is a shame, isn't it? Such a shame. So yeah, I've got the chat up, I'm looking at it, so if something pops up I will see it. So we're good to go. We are finally ready. Drop a yeet in the chat just to make sure that it works, and yeehaw. Okay, so just a fun, anytime you got questions, let me know. Expected value of x, we all know the formula for that by now. Howdy, howdy. But let me remind you that in terms of density function, so we have already talked about with expected value of x, your 1 over n, the sum of xi, right? We did that last time. Add up all the x's divided by the number of x's, or alternatively, the sum across the bounds of the thing times, or the thing times the probability of seeing that thing added up across the bounds of the thing. I don't know if this is familiar for you guys, throwing war flashbacks to that first midterm. But this is actually going to come in real clutch. We're going to remember that this e of x with the probability of x times x summed over the thing of the x was from when we had discrete distributions that looked like this, like probability that x is equal to a given x, hello, welcome, was equal to, the little brackets thing where it was, 75% if x is 0 and 25% if x is 1. Right, that's from the first midterm. We all remember that. That's, old news, old money, right? So we're not going to worry about that anymore. But the nice thing is, now we have graduated into a world where we are using continuous functions as probability densities, as opposed to just distributions, right? So now we have f of x is equal to, like, 2/3 x if like 0 is less than x is less than 24, I don't know, something like that, and then 0 else. Which is to say that the graph of x looks like, something, that one would be like a straight line or something. But we'll get there. But the thing to know for expected value of x and what has changed since the last midterm is that you will no longer be doing the sum of, from the bounds of x times the probability of x. Now what you're going to be doing is you're going to be doing the integrals over the bounds of x, we'll call them a and b for the lower and upper bounds of x, right? Of the thing, it's expected value of x is equal to the integral over the bounds of the thing times the probability of that thing, which has changed from just being a raw probability, like in our discrete distributions, the 0.75 and the 0.25, to being functions over certain domains. That is what has changed, and largely that is what we're going to test you on. That has been the subject of the change since the last midterm. I would like to point out to you again, though, that this is still the same formula, where above we did add up every iteration of the thing times that probability of seeing that iteration, right, xi potentially. Now it's just do the same thing but over itty-bitty tiny little divisions over the thing. That's what an integral is, right? We're just adding up all of the thing times the probability of the thing. That's what we're doing now, right? And so expected value of x squared is going to be the integral over the bounds of x squared times the probability of seeing that piece of x squared, right? That's, again, the same thing, but instead of using a sum and having like discrete values x equals 0, x equals 1, now we're going to do an integral over all of the possible values of x that occur within a certain range. You know, 0 is less than or equal to x, which is less than or equal to 1, or something like that, right? The same is true of variance, but like you use e of x and e of x squared for variance, so you can pretty much get it from there, right? Basic point of this early thing, passing e's and b's through, is that now we're dealing with functions, okay? And then like, let's say, for example, now I'm in a world where I don't get to just look at a table of like x's and y's, right? 1, 0, 0, 1, 2, 3. Like we've all seen those before, right? We don't get to look at tables for these probabilities anymore. Now we're looking at joint probability density functions, which is to say, now I might have a function that looks like 4/3 minus 4/3 xy, right? To pull an example from nowhere that I can remember in particular. What if I wanted to find the expected value of xy in regards to this function? Well, that's pretty simple, right? Also, let's recall that the bounds of x and y were 0 to 1. This notation means that both x and y are elements of the range 0 to 1, right? Once you take Math 290, if you want to get your math minor, you'll become intimately familiar with that notation. But anyway, well, what I can do if I need the expected value of x times y, wild guess, well, I'm just going to integrate over the bounds of x and over the bounds of y, the thing, xy, times the probability of the thing, dy dx. And I would work first from the inside, you know. I'd work on this integral first, and I'd have to do either I distribute the thing. I would recommend that you distribute the thing through, because if not, you have to do a chain rule, and it's really annoying. And then, so I'd do the derivative of y, the integral of y first, get y taken care of, and then I'd go outside to do the x's with whatever's left in the middle. Okay? Again, the thing, xy, times the probability of that specific thing, 4/3 minus 4/3 xy, over the bounds of x and y. Nothing new, we're just throwing a second variable in there now. And we're doing it with a function instead of with discrete, I know these values. We are now accepting ambiguity, which is fun. We like that. So let's see. Covariance and correlation tips and tricks. I'll just remind you really quickly that the correlation of x and negative 100,000 y is equal to the negative correlation of x and y, for reasons we discussed in our last review. But constants go away with correlation except for the negative sign. If it's double negative, of course, they will cancel each other out. We remember that from last time, of course. But if we are looking at covariance of x and negative 100,000 y, of course that will still be equal to negative 100,000 times the covariance of x and y, because constants do get pulled out of covariances. That's just a helpful reminder. We're not going to spend too much time on that. So now we're going to cover some fun things to do with probability density functions, and I'm going to use a problem that you guys have already been familiar with on the homework, but we're going to talk about it in a fun, new, exciting way. I've already talked about it, right? This is the, just because it's the one that I know off the top of my head is a legitimate probability density function. We're going to talk about why it needs to be like that as well. But we have f of x and y is equal to 4/3 minus 4/3 xy. Okay? For x and y both have the domain 0 to 1. Yeah, that's the domain. So the really nifty thing about this is, I don't know if you can tell, but this graph would be in 3D, right? Because on the one hand, you would have, you know, here's your x-axis, right? And there's some kind of fun probability distribution of x over there, going out, you know, towards us in this case, in the x direction. And then in the y direction, you know, you've got some sort of probability density there as well. But the actual value of f of xy would be on this like third axis here, and that would be what makes it kind of like funky, and it would give like curve to this. The whole reason that I'm telling you this, right, and let's just say that we have, you know, the bounds of y out here at 1, 0 to 1, 0 to 1 for x and y, like we see up here. The whole reason I want to show you this is because you're going to have to get really, really good at thinking about these probability densities in terms of graphs. Okay? You can tell from like the charts that you've seen with like the normal chart and the t-chart, the rest of the class is going to be dealing with charts and graphs. And so the way to think about a probability density function, especially this joint one right here, one great way to think about that is there's this like field of possible possibilities, right? So possible possibilities. If I took this point right here and said it was at like, you know, oh, let's say, you know, 1/3 at y and like 1/4 at x, then the point on the fun little like curvy surface of fxy, where it actually gives me the result, you can think of that as the probability of getting y equal to 1/3 and x equal to 1/4 at the same time. Fun stuff, right? So here's a fun little question for you. We have this like surface that is, you know, f of xy. It extends across the bounds of x and y, and it's raised because every combination has some kind of probability to them. If I were to ask you the volume of this shape that is between the x and y axis, so like the x and y axis as its floor, right? And then with its corners going up to the corners of the distribution, that it looks kind of like a cube starting, like a rectangular prism on the bottom, and then it's going up and it's probably curvy on the top. Do you want to take a wild guess as to what the volume of that solid would be? It would be 1. Why would it be 1? Yeah, so like, because each of these points represents a probability, we're never going to represent more than 100% of possible outcomes, right? Which we represent as 1. That is why, by the way, Kalel, this video gets automatically uploaded once I stop the stream, as far as I'm aware. So, but yeah, so the area underneath the joint probability density function has to integrate to 1, because it has to represent all of the possible possibilities, all of the possible probabilities, all of the probabilities of all the possible combinations. However you want to say it, it represents 100% of all total outcomes. There's a reason it doesn't go past x equals 1, because x can't go past 1. And you guys remember from the homework where we did this, where we changed it so that x and y were now from 0 to 1/2. You remember doing that, right? Basically what we did is we basically took these corners and just pushed them in the probability density function. And it like raises it up higher because it has to represent more possible, fewer possible outcomes means each outcome over there is more likely. And so you noticed it actually turned the function into, if you recall, or if you got help from me in office hours, it became 64/15 minus 64/15 xy, right? For x and y with the domains 0 to 1/2. Now, is the function like really different? No, it's not. It's still pretty much some constant times 1 minus xy, right? Still the same function, but when you adjust the boundaries, you have to adjust the function so that it always represents 100% and only 100% of all possible outcomes. And I started you with the hardest version of this here. It's hardest to picture this in like a 3D curved graph with like a rectangular prism with curves on the top of it. Like that's the hardest thing to picture right here. Way easier to think of it. In fact, let's just, way easier to think of it as like a normal distribution, which we'll talk about soon. What do you think the area underneath a normal PDF, which is what the bell curve looks like, what do you think that integrates to from -infinity to infinity? It integrates to 1, because this PDF represents the possibility or the probability of seeing every individual value of x in a continuous function. It's no longer discrete, because if it were discrete, the brackets would have to be like infinitely long, and it would be 0.0002 if x is equal to 1.00003 and 0.0002 if x is equal to 1.0004. You get what I'm saying, right? This is why we use functions and integrals instead of tables and sums now. So that's the first thing to start to keep in mind, okay? So what then is a marginal? In fact, let's come back to this picture right here. Just looking at this picture, maybe ignoring the green parts, what would be the marginal density of y? What is that? Like, explain it. Basically, what if I got rid of the x-axis? I took every point on here, right? Every point that's out here in the x-land, and I just moved them all onto the y-axis. That's what the marginal distribution of y is doing. Is it's taking a function of f of x and y, and then we are integrating the x out of it, right? 4/3 minus 4/3 xy dx. And when I do that, I'm left with just a function of y. I've taken all of these points and I've effectively just pushed them. And then I've adjusted to make sure that the area under the curve integrates to 1, as opposed to the volume that used to exist, right? A lot of weird stuff that I'm talking about, with the explicit purpose of I'm trying to get you to be able to visualize this. Because if you can think about it as graphs, you'll be in a really, really good spot. So let's just move on from this for a second. And let me just give you the concrete, how do I calculate marginal probabilities, okay? If I have this f of x is equal to 4/3 minus 4/3 xy, for x and y have the bounds 0 to 1, how do I get the marginal density of x? Integrate with respect to y. Why? Because I want to get rid of y. I don't want y to be a factor anymore. I don't want to even care about it. I don't want to look at it. It's ugly. It's disgusting. I hate it. I want it gone. And you know what's funny is that I'm in multivariable calculus right now, Math 314, and we've just finished the partial derivatives and integrals section. And we spent like 2 whole class periods talking about, aha, when we do this integral, is x a variable or is x a constant? And I'm just like, bro, we're only integrating with respect to y, so of course x we can treat as a constant here. We're not looking at it over a bunch of different values. We're just calling it x, right? So when I want to find this marginal probability, I'm going to evaluate this integral over just with respect to y, which means this is going to turn into 4/3 y minus 2/3 xy squared, right? Because I have to pull a 2 out from the denominator to put it back on the y squared, right? You remember how to do the integrals. And evaluate that over the bounds of y. So that means I'm going to plug in 1 for y. 4/3 times 1 minus 2/3 x times 1 squared minus parentheses 4/3 times 0 minus 2/3 x times 0 squared. We can see that this one will go away. The ones basically make it so that it's all just the same. And so we're left with the marginal density of x is equal to 4/3 minus 2/3 x. Cool stuff, right? Here's a fun fact for you. All right, here's a fun thing to notice. This is symmetric, right? And when I say it's symmetric, I mean if we had integrated x out, like we'd get the same function but with y's instead of x's, right? We can see why that's the case, yes? Phenomenal. So here's the question. Are x and y independent here? Fy of y is equal to 4/3 minus 2/3 y. We can all see why that's the case. Are x and y independent in this distribution? Natalie's saying no. Why not, Natalie? Because you have to multiply them together and it has to equal the joint distribution for them to be independent. Absolutely. And when we multiply these together, you can fairly clearly, in my opinion, see that this is not going to be equal to the same thing. Not least of which because you will get, as the multiplication of your late terms, 4/9 xy when you needed a 4/3 xy. So that's pretty interesting. Although actually I wonder, hold on. Let's actually check this. Because I'm pretty sure they are not independent. However, I have been known to be wrong at times in the past. 4/3 times 4/3 is 16/9. And then we have minus, and this is actually why it's definitely not correct. We have these 8/9 x and 8/9 y that we have to deal with, which is not helpful. X, there. Yeah, so very clearly this is not equal to that original joint distribution. So because we know the marginal probability densities, we can tell now they are not independent. Again, what did we do before? Well, before we just took p of x and multiplied it by p of y, and we checked if it was equal to p of x intersect y. Do we see a parallel here? Do we see a pattern? I hope you do, because there is a parallel, which is to say, f of xy, the joint distribution, represents the probability of having x be equal to a certain value when you have y equal to a certain value. It's just representing this over all the possible combinations of x and y at the same time. That's why the functions are cool. Because you don't need an infinitely long table, you can just throw it in a function. Super nice. We're going to do the same. We're going to use these pieces similarly to find a conditional probability. Let's just steal this again. I want to keep using the same equation. because I'm lazy and I don't want to come up with another one off the fly, because I don't think it would work. What is the probability that x is greater than 1/2 if we know that y is equal to 1/3, right? What are we going to do? What do I do with this? Well, fun fact, I know that this is going to be equal to the joint function of x and 1/3 over the y function, the marginal distribution of y, evaluated at 1/3. Now, why am I not dealing with the greater than 0.5 thing as I'm first writing this out? The reason is, as soon as I get it into this functional form, I'm going to have a function of just x, right? Because on the denominator, I'm only going to have a number, because to get fy of y, I'm going to have to integrate x out, so x will be gone. And then when I plug in 1/3 for every y will be gone. So I will be just left with a number. And then on the top, I'm using this function 4/3 minus 4/3 xy, but I'm going to plug in 1/3 for y. So I will be left with just a function of x and some other numbers. And then when I have that, then I can just integrate from 1/2 to the upper bound of x, and that will give me the total probability under the new x curve I've built, the area underneath the new x curve that I've built, which is the probability of all of the individual possible values of x from 1/2 to 1. So let's do that really quick. All right, we're going to do some fun math here. We know from the previous slides that fy of y is equal to 4/3 minus 2/3 y. Right, we just did that on the last one. I'm going to be speeding through this because there's other stuff I want to cover before you guys have to go. Basically, that means that fy of 1/3 is equal to 4/3 minus 2/3 times 1/3, which is equal to 4/3 minus 2/9, which is to say 12/9 minus 2/9 is equal to 10/9. Everybody see the math that I did there? Quick maths, right? And so I also know that f of x and 1/3, if I plug them in, is going to be equal to 4/3 minus 4/3 times 1/3 times x, which is going to be equal to 4/3 minus 4/9 x. So my conditional probability, f of x, given that y is equal to 1/3, is going to be equal to 4/3 minus 4/9 times x over 10/9, which means it's also going to be equal to this fun little thing I just drew right here in parentheses times 9 over 10, because dividing by a fraction means you can multiply by its reciprocal. Everybody remembers this, right? And so what we'll do, this 9 cancels here. This one won't. 4/3 times 9/10 is equal to 12/10, which is equal to 6/5. And then minus 4/10, which is 2/5, x. Okay? Here's a question. Could we check and see if this is legit by seeing if this integrates to 1 over the bounds of x? Could we do that? Is that doable? Absolutely, it's doable. Let's do it really quick just to make sure that we did our math right. Integrate from 0 to 1, 6/5 minus 2/5 x. Dx. I don't want to bore you guys, but this is going to be 6/5 minus 1/5 x squared, evaluated from 1 to 0. I feel like it's pretty clear to see that that's going to turn into 6/5 minus 1/5, which is equal to 5/5, which is equal to 1. Everybody not cool with that? Not chill with that?
6 over 5x.
6 over 5 minus, no, just, oh yeah, it is 6 over 5x, yeah. But again, we're just going to plug in a 1 for x,
Right.
So yes, you're correct, I did forget that. However, luckily, that will not make a difference. This is going to be equal to 5/5, which is going to be equal to 1. But that was not the question. That was not the question, right? We already know that 100% of the possibilities are represented when we look at x from 0 to 1. I want to know what percentage of the possibilities are represented when I only look at x from 1/2 to 1. So that's what I'm going to do. Let's get rid of that. And instead of integrating from 0 to 1, let's integrate from 1/2 to 1. That's going to be interesting. So let's do that. As Natalie pointed out, this is going to be 6/5 x minus 1/5 x squared evaluated from 1 to 1/2. So we're going to be left with, in the first one, 6/5 times 1, which I'm just going to skip and say is 6/5. I'm just going to tell you that the first one integrates to 1, right? Evaluating it at 1 gives us 1, right? Because we're going to plug, yes?
Is it 1/5 x squared or 2/5 x squared?
It's 1/5 x squared, because you remember when I took the integral of this x here, I have to turn it into x squared. And you know that the derivative of x squared is 2x, and so we have to pull a 2 out of here to make it square again. Yeah. Antiderivatives, totally fine. So from the first part, we've got 1. But now we need to evaluate this at 1/2 so that we can subtract it off. So let's do that. 6/5 times 1/2 minus 1/5 times 1/2 squared, which is equal to 1 minus 6/5 times 1/2 is equal to 3/5 minus 1/5 times 1/2 squared. 1/2 squared is 1/4. 1/4 times 1/5 is 1/20. That is going to be equal to 1 minus 3/5 is equal to 12/20, right? Everybody got that? Just multiplying by 4 over 4. 12 minus 1 is 11, so this is 1 minus 11/20, which is equal to 9/20. So, what does this mean? We've got an answer now. This means, cool stuff, this is the interpretation. I was asked for the probability that x is greater than 1/2 if we already know that y is 1/3. Okay? So, based on this above function, 4/3 minus 4/3 xy, based on, you know, this funky thing right here, this funky little solid that is this distribution, it's what is represented by. If you were to ask me, looking at this solid, if I only look at where y is equal to 1/3, so just on this slice right here, where y is equal to 1/3, where the shape maybe looks kind of like this along x, right? Something like that, okay? Then the question is, if I go out to x equals, you know, 1/2, and I'll do this one in red, if I go out to x equals 1/2, and I just integrate that, we have just basically found the area of this piece right here. This is what we have found. Cool stuff, right? I think it's pretty nifty. Geometrically, that's what that represents. But just literally in the world, what it means is if I know that I have sold, for example, 1/3 of a warehouse of good Y, you know, given good Y, then what is the likelihood that I have already sold more than half of my warehouse full of X? Well, the odds are not great, but they're not awful. It's 9/20. So it's more likely that I haven't quite hit half of the warehouse is sold yet, because I know I've only sold 1/3 of Y, and just based on what I've seen and how the probabilities look, which they look like that, just based on what I've seen over being a business owner, this is what I know is true, right? I have a 9 out of 20 chance of already having sold over half of my X's if you tell me I've already sold 1/3 of my Y's. That's maybe just a practical interpretation of this P right here, this one right here. Questions? Cool. That basically represents having covered this entire page. So let's draw a little smiley face there. And then what the heck is K? I don't want to point this out too hard to you or like drill it too hard into your guys' heads or whatever. I mean, there are some things that I do want to like just drill into your head. Like you can't have a negative variance, but this one's not so much. But notice that this K times 1 minus xy represents both this function and this function just according to different bounds. Right? So K is kind of like the squish factor, where if I have to take all of these points and squish them in to some different bound, I need to adjust the height of like the shape that it makes. right? Just so that it all integrates to 1. K is my little friend that makes sure everything stays legit. It's like, what is K like? K is like, you're like, if you go out to like the bar, I know this doesn't apply to any of us, but if you go out to like a bar, K is like your designated driver, where it just makes sure everything's legit, no matter what bounds you're trying to make happen. It's not a great metaphor, but that'll get the job done for now, I think. So now let's move on to the actual fun stuff, which is, yeah, hit me.
So the k times 1 minus xy, that's just like a specific function that is given in that specific problem, or is that like a general?
No, so the specific function that we were given is this one, right?
Yeah.
But it's pretty easy to see just from that function alone that it is 4/3 times 1 minus xy, right? And if I want to play with that particular function, the 1 minus xy times some constant, right? If I want to adjust the domains of x and y, I need to adjust whatever the k was that was operating there before. Because again, like, k is like the designated driver. It makes sure nobody like goes too far, which is to say, if I changed this fx of y to be 4/3 minus 5/3 xy, and I didn't change the bounds, this would no longer be a legitimate probability density function, because this shape would extend out too far, and the volume of the thing below it would be more than 1. So it's representing like more than 100% of all the possibilities, which doesn't make any sense, you know? You can give 100%, 110% at your job, but that's the only place. Everywhere else, it's just 100%, you know? Question.
So if a question was asking, so say they gave us 4
Sure.
and they wanted a function with different bounds, like how would a question like that be worded? Like how do you recognize that?
It won't be. It won't be. I just want to throw that out. Well, let me make sure that it won't be before I tell you and promise you that it won't be. But the reason I wanted to go over k here is because it helps you think of what these probability functions are actually trying to represent, because that concept is the hardest thing to get from this class, is like, what do the graphs mean with like probabilities that I've seen? How do I translate a graph into like 1/2 in my brain? One sec. Yeah, you won't need to do any k'ing here. But it is nice to just notice sometimes what the k's kind of do. So like, say for example, I've got the function 1/3 x plus y with x has the bounds of 0 to 1 and y has the bounds of 0 to 2. Where do you think the 1/3 came from? Right? Are we just throwing a 1/3 onto both x and y for funsies? Or is this more likely to be something like a k of x plus y that got figured out because of these bounds? Right? Because PDFs represent probabilities of individual occurrences, is the way that you're thinking about it. We have to adjust those PDFs if we make the possibilities of x and y different. We cannot represent more than 100% of possible outcomes. So if I add more possible values of x, for example, do you think k will grow or shrink? It will probably shrink, because we have to scale down all of the values to represent the fact that there are more of them possible now, right? That's probably enough on that. And then the one other thing I would like to point out is that what we did here in this question to get this 9/20th is we evaluated an integral from 1 to -1/2. I would like to point out to you that all that we did is we did the cumulative distribution function of x given y is equal to 1/3 minus the cumulative distribution function of 1, given that y is equal to 1/3, minus the cumulative distribution function of 1/2, given that y is equal to 1/3. That is exactly what we did here in this little bottom thing. We just skipped the step of calling it big F of x, given yada yada. That's the CDF. It's the cumulative distribution function, which is to say, of course, if I have a distribution that looks like this, and let's say I have 0 here in the middle, I could integrate from -infinity to 0 this PDF, which is what I have drawn, right? This is a PDF. Right? I could integrate from -infinity to 0, and that would give me the probability of getting a value that's less than 0. Because -infinity to 0 represents all of the possible values this PDF can take on that are less than 0, right? So we just find each of them individually and add them all up. Or I could just do big F of 0. Same thing. Okay? Because big F of 0, here's the fun fact. This is what the CDF of the normal distribution looks like. CDFs start at 0, right? So if I go all the way to -infinity on this PDF, and I start to integrate from the left, I'm going to start at 0. I don't have any distribution under the curve at -1 right? So it's small, 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 and then we get up to here, and we go like that. And this value right here, for the standard normal distribution, this is actually, I was actually wrong. They do not start at 0. The y values do start at 0, though. This is x, this is f, big F of x. So what does this CDF represent? Well, if I start at -1, Jed.
I was wondering, does the inflection point represent the mean here?
In this case, yeah, because the bell curve is centered at 0. And so what this represents here, this CDF, I'm going to show you with the fun little laser pointer. When I start at -infinity, over here at -infinity, -infinity, the curve is like basically touching, right? This is the tail. The tail is tiny. There's like 0 there, practically 0. And so when I start at -infinity and I start to add up all these little bits, so I'm at -infinity over here, the total value underneath the curve, which is what this line represents, the total value I've added up so far is very, very small. But then I start to get up into here, right? And now I've definitely added up some probability. I've probably added up a decent fraction of the probability. And in fact, if the bell curve is symmetric at 0, once I get to 0, and I've added all of that up, I'm going to be at exactly 1/2 of all of the possible probabilities, all of the possible possibilities, right? If x can take on a value from -infinity to infinity, and it's centered at 0, then once I integrate up to 0, I have represented 1/2 of all total possible outcomes, which means my cumulative, or I have accumulated, half of all of the probability that are possible. That's where the C comes from, the cumulative. I start from the left and I go until I get to the chi-squared, in which case I will start from the right and come. But we'll talk about that in a second, right? So that's PDF, CDF. That's it. And if you can keep these like graphs and like this idea in your head that like PDF, the probability is underneath, integrate, you're going to be good to go. And this thought process is actually going to be key to understanding the charts as well. Pardon. It's going to be really key to understanding the charts.
Just like if we want to just get a general PDF to a general CDF, we just integrate from A to X and sort of a double integration.
No, you don't actually do a double integration. That is a good thing for me to point out to you really quick. Let me just move these. Let me get that 0 in there really quick. Just move these boys over, give me some room. If I have a generic PDF, let's call it something that I know integrates to 1. Let's just say, for example, I have the PDF 1/2. right? Like this could be like a uniform. In fact, let me move into talking about the special distributions while also answering this question, okay? Today or yesterday you learned about the uniform distribution, which says that x is equal to 1/2. For example, a constant, if, you know, x is between, let me think about this, I think, yeah, it should be 0 to 2, and 0 if not. So what does this look like on the graph? Well, this PDF is not centered at 0. 0, bow, bow, bow. Let's call that 2, 1. This is the x-axis. This is probability of x, right? This is 1/2. That's 1. This is 3. This PDF looks like this. In fact, let me use a different color real quick. Looks like this, and it just ends at 2, right? What is the area underneath this curve? 1, definitely. I know that this integrates to 1. This is like, it's equally likely that it's between 0 and 2. It's basically random. So the one thing I'll point out to you, what is the expected value of x in this case? Where do you expect x to end up on average? Not at 1/2, because that's the probability of 1. Not 2, because that's the extreme one. It's 1, right? Just because in this case you're going to be doing, it'll be the integral from 0 to 2 of 1/2 dx, which will be turning into, you know, 1/2 x evaluated from 2 to 0. The uniform one is really nice like this. Yes?
Is this also like the one?
This is the AB one, yes. So that 0 and 2 right there are the A and B. Which is to say, if we want to do this in a generic form, then we would integrate from A, the lower bound, up to x, the real true x. The PDF, in terms of our fake imposter stand-in for just the moment x, right? Which will turn into 1/2 fake imposter x evaluated from real x to whatever the lower bound is, which in this case is 0. So this CDF would turn into, you know, big F of x is equal to 1/2 x, you know, minus 1/2 times 0, but it's equal to 1/2 x, right? And you can always check to see if it's a legit thing, because you should be able to do big F of B minus big F of A and get what? What should that turn into? One. Yes, it's 1! Why is it 1?
It's always fun.
Why is it 1? Because B is the upper bound. And if I integrate from the left to the upper bound, I'm capturing all of the possibilities, right? Capturing 100%. And if I integrate from the lower bound to the lower bound, I'm not integrating anything. So it's 0, right? So you can always double check if you've done this right by seeing if you've created your CDF correctly. F of the upper bound minus F of the lower bound, 1. Now you're going to have a really hard time with that if you try to do the CDF of a normal distribution, because nobody's figured out how to do it yet. That's still a mathematical mystery that nobody's close to solving, and we don't need to be, because we have tables, right? But so like this double check doesn't really work for that. But if you're doing uniform or like Bernoulli or whatever, go ahead and check. It's great. I won't erase that all, actually. So there's the uniform distribution, super easy. Fun fact, the CDF of this, notice that I have P of x right here on the top one when I'm graphing little f of x. It's because you think about them the same way, right? But over here I just have to put f of x because it's cumulative, right? Fun fact, no, hold on.
And then
Nope, it's like this. This graph looks like this. Wild guess why the value of it is 1 when it hits 2. Well, here's a fun question for you. If I plug in x equals 1 to my big F of x, what do I get? 1/2. And if I integrate, let's just erase those for a second. Not that last one though, I liked that last one. And if I integrate this from 0 to 1, what do I get? 1/2, 1/2. You see this pattern here, right? So if I integrate the PDF from the lower bound to a number, whatever I get, the area, becomes the value of f of x at that x that I integrate it to. I have accumulated 1/2 of all of the possible outcomes when I get here, because that's the area under the curve, right? So I have accumulated, how much? I've accumulated 1/2. Uniform is really nice to use to try to illustrate these kinds of things because it's pretty simple to look at and kind of understand. So let's move on from uniform now. Let's talk about Bernoulli really quick. I'm not even going to draw a graph of Bernoulli because she pretty much was supposed to have already told you about it. But basically just like the expected value of an x, if x is distributed. Okay, so actually the one other thing I need to tell you about. In this case, this uniform distribution can also be written as a shortcut. Here's how I want you to read. I'm going to tell you exactly word for word how I want you to translate these things when you see them. Okay? Translate them from math symbols to English like this. X is distributed as, so I'll actually wait for it, X is distributed as, that's what the squiggle means, a uniform random variable with lower bound A and upper bound B. I believe is what it's supposed to be. If you check your notes and it looks different there, my bad. I'm gonna be real with you, but that's what it is. X is distributed as a uniform random variable with lower bound A, upper bound B. And you'll always be able to tell what level it's at by just saying, you know, what's B minus A? That's the length of the line of B, right? 2 minus 0, that's the length of this. And then how high is it? Well, it's 1 over whatever B minus A is, right? 1/2, 2 minus 0. We can see that. Fun stuff to play around with. If I add up uniform distributions, what does it do? Well, we have to rescale things a little bit. Can I multiply them? I would encourage, you're actually going to find out more about that in the review tomorrow, so pay attention to that part because I can't 100% remember, but you should definitely pay attention to that part tomorrow. Just want to throw that out there just for funsies. No real reason. So yeah, let's talk about Bernoulli for a second. The only thing you really need to know, X is distributed as a Bernoulli random variable with parameter, you know, P. That's just the probability that X is equal to 1. In the example that she always uses, it's like a 0.56 or whatever. Probability that X is equal to 1 is 0.56. The probability that it's 0, bless you, would be 0.44, so on and so forth. Expected value of X in this case, I should probably show you this for uniform as well. Expected value of X for the uniform distribution is just 1/2 of, it's just the middle value. It's 1/2 B minus A. Just because, like, if I average this, it puts it right in the middle, just for fun. That's just how it works. That's just how an average works, right? 0 plus 1 plus, you know. Anyway, that's a whole thing. And then the variance of X for this, I don't 100% remember what it is. but it's something like, I'm not even going to give it to you. Just pay attention tomorrow. Pay attention tomorrow in the review to that part in particular for no particular reason. But with Bernoulli, the expected value of x is just p. So if x equals 1, 56% of the time, the expected value of x is 0.56. I expect to succeed at x 56% of the time, you could say. And then the variance of x is actually just p times 1 minus p. That's using the whole expected value of x squared minus the squared expected value of x thing. It just so happens to also work out to be p times 1 minus p, which is easier. But if you get lost, you can always do e of x squared minus the squared expected value of x, right? You can always do that. That function never fails if you do it correctly, which is a caveat, but just know that. So yeah, it should all be on the formula sheet as well. In fact, that's actually a really good point. Most of this can be on the formula sheet. I'm gonna be real with you. I have no idea how you would do that, but if you managed that, I would be personally extremely impressed. The sheet's not actually at the end of the, oh, here it is. Yeah, there's no preview. I'm looking at Overleaf. It's not working. But anyway, 7:06. Some people have to go at 7:30. So let's cover the actual meat of everything, which is normal, t, and chi-squared. If you've got your charts with you, you're going to want to pull them out. I'm going to pull one up on Learning Suite really quick so that we can use it. Let's go to Learning Suite. We're going to log in. And I'm going to switch to student mode so I don't accidentally show anybody's grades. But we'll go to Content. We'll go to Distributions and Estimators. Download the PDF. And here we are. We have our tables. So, the fetch do all of these mean? But don't worry, we're going to talk about it. No need to get too crazy yet. Yeet. Cool. That'll be great. First, we're going to talk about this Z table. One thing I would like to stress to you about this chart is that it is intuitive if you can learn how to use it. Okay? Which is to say, there is a reason they have highlighted things that are to the left of a Z-score. Okay? We'll get more into this after the midterm, but I would just like to stress to you that the reason that it is highlighting these things is because if I pick a certain Z-score, this table, let's say for example, just zoom out just a titch. Let's say for example, I don't have a little highlighter over here, unfortunately, which I would actually love, but I don't have that in Safari. So let's actually just look at this circled value right here. This is 1.0, 1.0, and then the column it's coming from is the 0.00 column, okay? And now it's going to be too small for you guys to see, but you have your tables. You know that the Z value in the middle of the table for a Z score of 1.00, that's how we read this Z table, is, so like, the Z score, if I set Z equal to 1.00, then the Z score is equal to 0.8413. Okay? You saw that circled one. You saw how I found that, right? If I wanted to find the Z score for Z is equal to 0.64, I would come down on the left side to 0.6, and then I would go over to the 0.04 column. So this is the 0.00, 0.01, 0.02, 0.03, 0.04. 0.73 something, right? That's what it turns into, okay? What is this Z-score in terms of this graph? What is it?
The integral.
The integral of what? You're right, you're on the right track. The integral of what from where to where? Not from 0, because remember normal is centered at 0. Yes. The integral from -∞ to Z of the standard normal table is equal to 0.8413 when you set z equal to 1.00, approximately. Okay? What does that mean? Practically what it means is you have an 84.13% chance of getting a z-score that is less than 1. Makes sense. This makes sense intuitively as well when you look at the normal distribution and realize it goes from negative infinity, takes a bump at 0, and then goes out to infinity and basically looks like this, right? If I have gone, and here's 0, I've come from negative infinity, and I actually got over here to 1, I took this whole integral, it's pretty clear I've got most of the probability at this point, right? I've got most of the possible outcomes by like a long shot, because these tails right here are like definitely not to scale. They are way closer to that axis than I can even draw them. So yes, that is how we read the z-table, right? I would like to point out to you as well, this is a special kind of z-table. This is not your grandma's z-table. This is the standard z-table. In fact, z is the special variable that they give to the standard normal table to just stress to you how special it is, even though it's called standard. Why is it called standard? Because it's standardized. Let's say, for example, let's pull this away. Let's say, for example, that costs for maintenance or for upkeep or whatever, maybe wages as well, who knows. Let's say that I run a business and I figure out, I track my expenses and I track the repairs and all sorts of stuff like that. I track hours worked, and I come to find out that the costs that I pay every week are distributed as a normal variable with a mean of, let's say, 400 and a variance of 20 squared, or 400, which is to say the standard deviation was 20, right? This should look familiar from something. I don't exactly know what. Something like a homework or something like that. Who knows? But if I have found that this is true for my business, that it looks like costs are approximately normally distributed with an average of 400 per week and a standard deviation of $20, am I going to be able to get my probabilities from this table, just in this raw form? No. Why not? Because the normal distribution I'm looking at is not centered at 0. It's centered at 400. And it does not have a standard deviation of 20, as indicated by the width of the tails, or a standard deviation of 1, which would be indicated by the width of the tails. It has a standard deviation of 20. So this table is not for my company. My company has a different kind of normal distribution. However, I can standardize my company's normal distribution into a standard normal by taking, whatever number I want to play around with, subtracting the mean, or the expected value parameter, and then dividing by the standard deviation. So if, for example, I wrote costs minus 400 over 20, that is distributed as a normal random variable with a mean of 0 and a standard deviation of 1. Fun fact. So now that I've done that, I can use this table. So let's say, for example, I don't like to go over budget. So I want to be really cautious with my budgeting. So my question is, what is the number, let's call it Q. What number Q would I have to pick on my company normal distribution so that my chance of going over Q in a given week is only 5% or smaller, right? 5%. How do we do this problem? Well, let's think of this for a second really quick. I want the probability that I want the probability that costs is greater than Q to be equal to 0.05, or 5%, right? This follows from what I've been telling you, right? Because costs is still the variable here. I want to set a value at a constant Q. We will call this in the future a critical value, but we'll get there. I want the probability that costs, the random variable, end up being greater than Q, the number that I pick, to be 5%. I only want to go over budget 1 out of every 20 weeks, is to say, right? How can I solve that? Well, I know that the probability that Z is greater than X, or actually, pause, let me back that up. I don't know the distribution of the costs normal. I don't know those probabilities. But I do know the probabilities of the standard normal distribution. So the probability that costs minus 400 over 20 is greater than Q minus 400 over 20, I would also like to set at 0.05, if that makes sense. Now, when I have a random variable like costs, and I subtract the mean and divide by the standard deviation, that turns into a z-score, a z-value, if you will. Not a z-score, because the z-score will be the probability, right? And when I do that to Q, it's just going to give me a number. So I'm going to just leave it in the form Q minus 400 over 20 needs to be equal to 0.05. So we're almost there. I'm very close, because now I'm in the world where I know the distribution of a number that I picked. I know what it would do, but I don't have anything to compare that, that number that I picked to, right? So what is the z-value such that the probability that z is greater than that value is equal to 0.05? Someone take a look at the table, throw something out to me. See if you can figure it out. And for those of you at home, do that as well. Someone wants to throw out a super chat, you know, donate $10. Maybe you'll get a better score on your test. Just kidding. That would not be cool. And I would never do that, quite frankly. See if I can give you one more hint, okay? And I cannot stress this enough. Does the z-table give me probabilities that are greater than a value? No. So the first thing I would have to do, if I want to figure this out, I want the probability that z is less than this value, or that I come in with costs under my budget, to happen 95% of the time. Now, where is that value? Question, do I take z and on the left column go and find the part where it is 0.9 and then walk over to the 0.5 column? Is that what I do? Why not? The probabilities are in the middle, and the probability that z is less than this value is 0.95. Numbers.
Standard deviation.
I mean, yeah, they're technically in units of standard deviations, right? Because you're dividing by the standard deviation. Yes. But just think of it as like the z value is the thing that I pick, and the z-score is the probability. The z-score is the area to the left of the value that I pick. Always. Okay?
So the variable minus the mean over the standard deviation equals your z-value.
Yeah. So if I take the variable and I subtract the mean, divide by the standard deviation, it turns it into a z. Just straight up z. But if I take the number that I pick and subtract 400 and divide it by 20, which is subtract the mean, divide by the standard deviation, that will turn into a specific z, right? Because again, costs here is the variable. Q is a value that I want to pick, a constant. Yes?
So there's not like a specific point.
Mm-hmm. Yeah.
Both of the two values are
They're both.
equally distant.
Yeah.
So if you just pick
Convention says to pick 1.65, or actually 1.64 is the convention. It won't matter that much, which is nice. 1.64 is what we're going to pick here. So star in this case, we know that the probability that z is less than star, and where star is equal to 1.64, is equal to 0.95, which is the same thing, I just want to throw out there, 1.64, as saying that the probability that z is greater than 1.64 is equal to 0.05, right? This is just a classic 1 minus, right? We can see that? Excellent. So, I'm very close. How do I pick Q? Set it equal to the z-score. Well, the z-value. That's okay. That's okay. That's why we'll call them critical values in the future. But for now, yes, take Q minus 400 over 20 and set it equal to that z value. Because if I do that, notice that these two equations right here, I'm going to laser them. Notice that these two equations right here are identical. There is nothing different about these two equations except for the fact that in the top one, I haven't picked Q yet. Which means if everything else is equal about these equations, Q minus 400 over 20 has to equal 1.64. The equations are the same, right? So when I solve for Q, right, I get Q is equal to 1.64 times 20 plus 400, which is equal to, if somebody would like to not make me get out my calculator, but I'm already doing it anyway, so don't worry about it. 413.8. 432.8, right? Q is equal to 432.8. What does that mean? Somebody tell me what that means.
That means if you budget $432.80,
yes,
then you will only go over budget about 5% of the time.
Exactly correct. Perfectly exactly correct. That is what this is. If I budget 432.8, which is to say, I pick, Q, my budget at $432.80, I will only expect to go over budget 1 out of every 20 weeks, 5% of the time, about. Now, does that mean that will happen? No, because life is random, and that's what makes it fun, but we've got a pretty good shot if we pick those numbers like that. So that's great, good stuff. It's 722, so really quick we're going to do chi-squared. Fun fact, let me actually just touch on this really briefly. If we come over to the t-chart, I am just going to show you the difference between the z-chart and the t-chart, and then you can take all of the things that we've just talked about with the z-chart and do the same things with the t-chart, okay? They are functionally the same chart, except, I don't have a t value anymore. What I do have, okay? Notice up here in the drawing that instead of a z that I pick, and just to the left of it, what I actually have is a couple different letters that I can pick. I could pick a T, or I can pick a C. From the drawing, and from the column, let me point out to you, that C up there would represent the percentage of the area under the curve between a T and that negative T. What does that mean? Well, take a look at this. I really need to get a highlighter that I can use, like a little laser thing on like Safari. That would be really good. If I set my T distribution such that, well, actually, no. I need to pause. I need to bring this back. How can you tell that these middle digits are not probabilities? Because many of them are greater than 1. So what do they have to be? They have to be t values, right? They are the numbers, t star or negative t star, that I am putting onto this chart, okay? These are the z's. of the t distribution, right here in the middle. On the z chart, you have z's on the left and across the top. That's how you pick your z values. And you have probabilities in the middle. On the t chart, that is not the case. On the t chart, you have degrees of freedom on the left. You'll recall that the t distribution, that you can have a random variable, let's call it happiness, is a random variable distributed as a t random variable with degrees of freedom, that symbol thing, which we will talk more about later. But just remember that the expected value of happiness in this case would be equal to whatever the degrees of freedom is, and the variance of happiness, if I'm not mistaken, I am mistaken, the expected value of 0 of happiness, and the variance of happiness is the degrees of freedom. Definitely double check that in the review tomorrow when you come to class, but I am 90% sure that is the case as far as I recall. The reason I know that the expected value of happiness is 0 is because the t distribution is also centered at 0, just like the standard normal. But what happens is as I get more degrees of freedom, the t chart starts to look more and more like the z chart. What does that mean? Well, notice if I just pick t, and I ignore negative t and I ignore c, it's basically just like picking z. I could pick that t such that I have 95% of the distribution to the left of it, for example. In fact, let me draw this because this is really important for me to get across. Right? Say I pick a t here that has 95% of the distribution to the left of it and 5% to the right of it. Okay? And let's say I have degrees of freedom equal to 13. Okay? What is this t value? Well, there's a couple different ways I can get it. One thing is to recognize down here, at the bottom of the chart, it gives me one-sided p-values. And up at the top in the drawing, it says that the one-sided p-value is to the right of this t star that I've picked. Okay? So, if I want one side of the distribution to the right, like it says on the drawing, to have 0.05, 5% of the total probability, then I come over here, the one-sided column on the bottom, to the 0.05, and then I just go up to the degrees of freedom, and the t-score is 1.771. Later, Jed. See you tomorrow.
Later. Thank you.
Yep. T is 1.771. Let's also look at this for a second. If I took that t is equal to 1.771, and I put t, negative t, negative 1.771, how much of the distribution do you think is to the left of that number? What percentage of the area? 0.05. Why? Because it's symmetric. You can tell because they use the same variable there, right? Okay. And how much do you think is in the middle? This C. 90%. Notice, please with me, really quick, also, what's the total of the two tails then? If I have 0.05 at either tail, that's equal to 0.1 on the two tail. So notice with me really quickly, the one-sided p-value is 0.05. The two-sided p-value is 0.1. And the confidence level C is 90. That's how you read this chart.
Also, variance is fancy video overviews.
Ah, thank you. Yes. Variance is the degrees of freedom over the degrees of freedom minus 2. Yeah. No problem. I didn't get to chi-squared, but she will definitely do chi-squared in the review tomorrow. Also, you can watch this. I'm about to do it, so just pull up the end of the video. Yeah. Absolutely. Later, Natalie. Okay, that's how you read the t-table. I'm not going to do like another problem with it because, again, if you can just get this, if you can get to read the picture in your head and you already know how to do the z-table, you're golden. You're good to go. Okay? And then the last thing let's talk about is chi-squared. And then after that, we're basically good to go for all intents and purposes. It's the last thing that we're going to do. So, chi-squared, you will notice, the following. In this picture, first of all, this distribution is not centered at 0. That's a fun thing to notice. It is not symmetric by any means. Also notice that now the highlighted region of the graph is to the right of the chi-squared alpha critical value that we're going to pick. Why is there a chi-squared alpha? Well, fun fact, I don't know if you can tell super well in like the document that you have, but there's an alpha in there. This alpha right here is the area under the curve that is highlighted. Okay? That's going to be crucial to how we read this chart. So, we have degrees of freedom again, right, on the left. We're comfortable with that from the t-chart. And then over here at the top, we have the different levels of alpha. So walk through this with me really quick. Let me draw a big chi-squared chart, and we'll do it in like dark blue just for funsies. There's my chi-squared. If I set my chi-squared alpha with alpha equal to 0.995, where is that going to fall roughly? Is it going to fall here, or is it going to fall here? Way close to the y-axis. Why is it going to fall that close to the y-axis? Well, yep. Because we have 99.5% of the area under the curve to the right of this chi-squared 0.995. That's a value I can pick. So just have alpha here in the middle, right? I believe with chi-squared, by the way, I'm just going to throw this out here. You can check the notes. I would actually appreciate it if you check the notes. Let's say that, I don't know, let's just say that big Q is distributed at, in fact, let's call it W. W is distributed as a chi-squared random variable with degrees of freedom, that thing, which I don't remember. I really should remember it at this point, but I don't, and that's okay. I believe that the expected value of W will be this little v thing, yep, and the variance of W is going to be equal to 2 times that v thing. Good. We would have done that in class today, so shows you how much I pay attention in class. So much attention being paid by me, absolutely.
And those values will be on this sheet.
Yeah, they should be on the sheet, absolutely, which is great. So then in the review, again, how do you know that these numbers in the middle of the table are not probabilities?
Still greater
Many of them are much greater than 1. In fact, you'll find chi-square values on the homework tonight as big as 23. They get way bigger than that as well sometimes. If you have really small degrees of freedom, or really large degrees of freedom, that is, then those numbers get absolutely enormous, right? Don't get tripped up by chi-squared because it's flipped. Reading the chi-squared table is exactly the same as reading the t-table. If you can just remember which parts are filled in. Heck, the one-sided p-value on the t-table is even coming from the right. You know, this one-sided column down here, that's coming from the right. So don't get tripped up. Don't get tripped up. What do these tables mean? Well, if I want to pick a t such that the probability of being greater than that t is equal to 0.01, then I come to this one-sided 0.01 column, right? How many degrees of freedom did I have? Let's say I have 1,000, and I set it equal to 2.33. And if I do that, and I have a t distribution, if I have a t distribution, right, there's 0, and I set t equal to 2.33, right, 0.01 to the right, 2.33, That will give me 0.01 to the right, 0.99 to the left. Yeehaw. I'm done. Then I can, if I have a t-distribution in my problem instead of a normal distribution, I'll have the degrees of freedom to work with. Then I take costs minus 400 over 20, and you'll know that it's a t because it will say it's the sample standard deviation, but we'll get there. In this case, we'll just tell you it's a t. But then I'll take cost minus 400 over 20, and instead of doing this x problem that we did, I'm going to set q minus 400 over 20 equal to that 2.33. You know, assuming that this is no longer 0.05, that it's 0.01, right? That's how you pick these values, okay? The two things that I want you to look out for in the review tomorrow, because we are out of time, and I do want to wrap this up, even though if I make a longer video, I get more watch time, which is always great for the algorithm. We love that. But you'll be able to find this again to review. You can go to tmorg.org, and there's links to my YouTube, you know, on there now, which is super cool. So I don't even need to get the custom URL. Just go to tmorg.org, and bottom of the front page has links. Pretty for chi-squared? Yeah, let's do it. Let's absolutely do it. Let me go think of an example really quick. I'm just gonna come up with one basically off the top of my head. And it's going to be super cool, and you're going to be wondering, like, wow, where did he get that cool of a question? Like, holy moly, how did he think of that? Let's say, for example, let's use W again for no particular reason, and let's make it purple. Let's say that W, let's use a thicker pen. Let's say that W is a random variable and is distributed as a chi-squared random variable with degrees of freedom, let's say, how many degrees of freedom do you want? 32, maybe? Maybe you don't want 32. Maybe you want 28. I like 28. Can we find, first of all, what is the 95th percentile of W? Just going to throw that out there. How do I translate this question into regular English? Well, here's how I'd do it. I would say, okay, 95th percentile of W. That means I need to pick a value of W. And I know that that value of W has to be bigger than 95% of all of the other values of W. That's what percentile means. So, what's my alpha going to be in this case? If I know that chi-squared looks like this, with alpha to the right. And here's the chi-squared alpha. What is alpha in this case? 0.05. Absolutely. Set alpha equal to 0.05. So here's the question. What is the chi-squared value with an alpha of 0.05 at 28 degrees of freedom? Well, chi-squared 0.05 at 28 degrees of freedom is equal to, come to the chart. Am I on the left page? No, because these all have alphas that are in the 90s. And that's not what I'm looking for. So I come back over to the right. I say, okay, where is the chi-squared 0.05 column? It's this column right here. Holy moly. I come back. Degrees of freedom, I need 28. So let's go down to the 28 row. Here it is. I'm in the second column. I'm in the, it looks like the value is 41.3372. So that's pretty cool. What does that mean? What it means is if I were to have a chi-squared looking thing that I wanted to play with, some variances, right? I would say, okay, what then is the value of chi-squared with this given distribution such that 95% of all other possible values of chi-squared are smaller than that value? It's 41.3372. Great. Excellent. Phenomenal. We love it. Wonderful. what if, let me just throw this out here, what is the standard deviation of 2 times W? That's pretty interesting. Well, what's the standard deviation of just W? Also pretty interesting, right? We don't know that off the top of our heads. But what's the variance of W? Two times 28, which is 56. So what about the variance of 2W? That's just 4 times the variance of W, right? Yes, no, maybe so. Okay. 4 times 56 is whatever. Let's just ignore that for a second, because the standard deviation of 2W is just the square root of this. So it's going to be equal to 2 times the square root of the variance of W. Right? Because if I have a 4 inside the square root, and it's just multiplied through, I can pull it out and turn it into a 2, right? I'm allowed to do that. Math says so. So that would be equal to 2 times the square root of 56. Cool. That is the standard deviation of 2W. Notice that it's twice the standard deviation of W. So that must mean something, right? I bet it means that W times W, or if you have 2 different W's that are both chi-squared distributions, I bet if you multiply them together, then that is also a chi-squared distribution with degrees of freedom, the first degrees of freedom times the second degrees of freedom. Or the first degrees of freedom plus the second degrees of freedom.
Okay, so you're saying that W1 times W2 is distributed as chi-squared into W1 plus W2.
I believe that is the case. Because what is 2? Oh no, so it's not W1 times W2. It's W1 plus W2, right? Because in our example we did 2W, which is like W plus W, right? And we found the standard deviation. We found that the variance was 56, right? And the variance of this other one was 4 times that, right? So it must be the case that W times W has a chi-squared with variance, degrees of freedom. Let me see. Let me think about that really quick. So if the variance, it's 2 times, yeah. This is how I know this is the case. Okay. No, that doesn't make any sense. Hold on. Because the square root of the variance, because variance is equal to 2, yeah. Because then the variance of 2W is equal to 2 times 2W, which is equal to 4 the thing. And the expected value of 2W is equal to 2 degrees of freedom thing, which is what we found. So basically, pretty sure this is true, the W1 plus W2 thing. Again, this is the stuff in the review you're going to want to pay attention to. These fun little special properties of adding and subtracting these things. But also, I think you will have done something like this on the homework tonight as well. Yes. So go back to that, because I don't remember. Yeah. So W1 plus W2, if they're both distributed as chi-squared with degrees of freedom thing 1 and thing 2, then adding them together is also chi-squared with degrees of freedom thing 1 plus thing 2. Cool stuff. We love that. I don't know about subtraction. Don't ask me about it. And I promise I won't ask you about it.
Yeah.
Maybe. On the, who knows? Yeah. You are so welcome. Just, these are things you will have already done on your homework, so I'm like assuming they won't be too crazy. But the things that I think are most important, the things I think are most critical, just overall, from the last midterm to this one, just to wrap up, the things that are most important taking a joint density function and turning it into the two marginal densities, using marginal densities and the original joint density to find conditional densities. Taking those conditions or marginals or whatever you've already done and turning those into cumulative versions of themselves. So like you could have a cumulative joint with a double integral, or a cumulative conditional. If you build the conditional in and then integrate it, that's a cumulative conditional, right? That's important. Then still you have to remember how to find covariance and correlation, which means you need to remember this, this little expected value trick that I've been talking about for a while, that it's, the thing times the thing. Well, okay, it's the thing times, I actually erased it, but please remember the expected value of xy in this case would be equal to, over the bounds of the two parts of the thing times the probability of those things happening at the same time, integrated over the bounds of both of those things. Can't put too fine a point on that is what expected value is. The thing times the probability of the thing over the bounds of the thing. I'm going to beat it into you. If it so help me. I mean, I won't. I would never. That would be unkind. But that's important because you're going to need it to find correlations and covariances, right? All your formulas for that. You all remember expected value of x squared minus the squared expected value of x, expected value of xy minus the expected value of x times the expected value of y. That's easy for you now. You did that in the first midterm. You rocked it. Easy peasy. Your conditional things, remember that, of course. Let's think. If you can take that budget problem that we did with the 40-20 thing, and if you can use the way that we thought about that in terms of like, what is equal to what, I want to pick Q and costs is random, pick Q. When I subtract the mean and divide by the standard deviation of the random thing, it turns into Z. And when I subtract the mean and divide by the standard deviation for the thing that I'm picking, it should turn into some number from the chart. If you can remember that, you'll be good to go, right? If you can remember how to read the table so that you can pick that value, how we picked that 1.64 when we did that problem, you're going to be good to go. You can take a uniform distribution, and this is going to be something to think about tomorrow. Think about the uniform distribution and think about what might happen if you added them together. I'm going to leave that to you guys for an exercise. But what if I took, let's say x and y are independent, and I have this x uniform on 0, 2, which is what this means, right? X is distributed as a uniform variable over 0 to 2, or x is uniform over 0, 2, right? If you can take that, and then maybe say we have some y that is independent from x, that's uniform over 6, 49, how would you turn that into a joint density function, Think about that one. See if you can parse that out of your notes from uniform and stuff like that. Pay attention to that in the review tomorrow, definitely. If you can do expected values of uniform distributions, again, that one's super easy because it's just right down the middle. Should be good to go. Remember how to go from a PDF to a CDF. Remember what plugging a value into a CDF means. That's why we did these graphs here with uniform, right? Think about this relationship between this graph and this graph. Think about the relationship between, what this joint PDF means and what its integral would be, Think about that. Keep that in mind. Also, please don't forget that the median is just the 50th percentile, and that the mode is like the peak of the PDF, right? If I have this normal distribution right here, the standard normal bell curve, what is the modal value of this PDF? It's 0. That's the one we expect to see the most often. It has the biggest probability of happening, right? Keep that in mind. You could, but basically, if you're using For the mode, yeah, you'd do a derivative, but we won't actually ask you to do that. If we asked you for a mode, it would be like on one of these things that we draw you pictures of.
Okay.
So like in the chi-squared distribution, the mode is the expected value because it's the degrees of freedom, because it's the big, I don't actually know if that's the case. But I do know that like the mode is 0 for the standard normal and for t, right?
So for like a uniform
Mhm.
distribution,
There is no mode. They all occur exactly equally, so actually every value is the mode.
yeah, I see it on that one.
No, because 1/2 is the probability, remember. In the one that we drew of uniform, it'll come up in a sec. We'll get there. I screwed it away. And then 1/2 is the probability of seeing this value. 1/2, 1/2, 1/2. They're all equally likely, which means none of them are modal.
Oh, yeah.
But the expected value is 1 just because like it'll all average out to turn into 1 eventually, which is cool. Yeah, standard normal, you can add up the variance and just pass an E and a V through if you're adding up standard normals. You did that on a homework with like the x plus y, x minus y, 2x minus 3y. You remember that from 2 homeworks ago, maybe 1 homework ago. Keep that in mind. And then the other nice thing is if you standardize 2 things that are distributed normally, if you find the 95th percentile z value that you need to pick for one of those things, you can also use that value for the other thing. Just instead of multiplying by the first standard deviation and adding the first mean back to that new z-score that you've picked, and by z-score I mean z-value, right? To that same z-value, multiply by the second standard deviation and add the second mean, and you will have functionally equivalent values for the 2 distributions, right? If you can just think about it from the perspective of this example, where I'm running a business and I have costs, and this is my distribution. It's a different distribution from the rest of them, but I can always get to standard to help me pick values. If you can just keep that in mind, that'll be good. And you're pretty much good to go. Okay? And those are all just things that I felt were important to share with you. Just, some kind of inspiration. You can, yeah.
Right here,
Yes.
this is a z score.
Yes.
This is a z value.
Yes.
Got it.
Z-scores are probabilities. I don't actually know if that's true, but just use that for now. Because actually, the z-score is probably actually just a z-value. And actually, I was wrong the whole time. They are p-values, is what they are. P for probabilities. Yeah. So, z-score. The reason that you know it's a z-score is because something that you pick turns into it. So, the z-score of Q in this distribution is 1.64. So unfortunately, I have spent the entire time saying that wrong, which you would think I wouldn't do anymore, this being like the 3rd time that I TA. But what can you do?
It's okay, you have me convinced this is like the 4th stats class.
Yeah, I know. So p-value is the probability. So pick a z-score or a z-value that gives you that probability. As long as you can write it out like this, you go over the video again, and just every time you hear z-score, substitute p-score in there, or probability, whatever. Just go back, but this is the framework. If you just mute what I said, even, just mute the video, and just watch me draw this slide, that is the process that will get you the answer on all of these. So,
Thank you.
yep. Thanks for coming. Have a great one. Oh, will do. I think she's out there, so if you want to say hi. All right, thanks for watching, everybody. This will go onto the channel. I'll make sure to send out a link to the video to everybody as well, but if you want to get it quick, you can just stay if you're watching. And if you're not watching, that's just a darn shame. So, thanks. Also, I can't believe, will this video be uploaded later? Khalil. Who do you think I am, Khalil? That's okay. All right, we are going to end this now. Thank you so much for watching. Subscribe, hit that bell, give it a like, do whatever. Always helps. and we will see you around. Thanks for coming to lab hours, and we'll see you next time. Adios.